Congratulations, everyone. You survived Unit 6, sampling distributions, and we're going to take a little pause in Unit 7 to talk about confidence intervals. So confidence intervals, I think, are going to be a little bit more intuitive, make a little bit more sense, and they're really quite cool and powerful and commonly used in a lot of different places, okay? So let's start by putting this chapter, this unit about confidence intervals. What are confidence intervals? Let's start by putting that in context. I was going to try to make a joke that didn't work. Anyway, so we have two main ways of guessing information about the population proportion P. We're doing inferential statistics right now. We want to know the population proportion, but we can't find it unless we take a census. We can't find it unless we look at literally all of the data. So what we do in statistics is look at some of the data, the sample, and then generalize that to the population. And currently, we've just been doing this. We can take a sample and get a sample proportion P hat, which should estimate P, right? If we're doing good sampling methods and minimizing bias as much as possible, we can get, hopefully this should reflect what P is. That's the whole point of taking samples. And this is what's known as a point estimate because it gives one number to estimate P. But it doesn't really tell us how sure we are that our estimate's a good estimate, right? If I take a sample of 5 people, I could get a P hat. If I could take a sample of 50,000 people, I also get a P hat. And sure, I could tell you the sample size, but it doesn't really give us a good numerical picture of how good this is. Now, hopefully I've piqued your interest because now we've got the good news. We're going over here now in number 2 to introduce confidence intervals, which is another way of estimating P. So specifically, here's what we're going to do. We're still going to take a sample just like before, and we're still going to get a P hat. We use that P hat to get an interval of reasonable values for P. So not just one value that P might be, but an interval of reasonable values for that population proportion. It's known as an interval estimate, and it does tell us how sure we are that our estimate is good. One of the things that we're going to be saying roughly later on in this unit is something like this. We're 95% confident that P is between some number and some other number, okay? So it still gives us an idea of what P is. Yeah, P is probably about 47%. P is probably about 0.47. But we can be 95% sure that it's between these two numbers. So we really get a kind of a bigger picture or a better picture of what's going on. That's kind of the overview of what we're doing here with confidence intervals. Okay, so before doing that, we're going to be needing standard deviation of a sampling distribution. And you remember from the previous unit, I'm sure, that the standard deviation of a sampling distribution is calculated like this. For proportions anyway. Unfortunately, we don't know what P and Q are. That's the whole point of this unit, confidence intervals, estimating what is P. So we don't know what P is, so we're going to estimate it with P hat. So instead of finding our standard deviation of our sampling distribution, we're going to get an approximation of our standard deviation for a sampling distribution, and that approximation is our standard error. Okay, so again, we don't know the standard deviation of our sampling distribution, so we'll approximate it by just replacing the P's, which we don't know, with P hats, which we can find from a sample. P hat, that point estimate, that estimate of what P is from a single sample. So we'll be using this to approximate, and it's called the standard error, and this is how it's written. Again, this is kind of like function notation. If anyone's ever seen this written, f of x, it's not multiplication, it's the same idea. This is taking the standard error of P hat. The notation's not very important for this class, but if you were wondering. So let's do an example here, okay? So we took a survey of 2,500 HR professionals, pretty big sample size, liking how this is starting. So took a survey of 2,500 HR professionals, and that survey showed that 1,200 of them use social networking sites when they research job applicants. Okay, so almost half of the HR professionals that we looked at will use social networking sites when researching job applicants. And yeah, maybe this is probably a lot of this is LinkedIn, but this could be other social networking sites as well. Again, as always, general reminder, be careful what you put on the internet. Okay, so state the sample proportion and then calculate the standard error, which remember we just told you what standard error was up here, for this sample proportion. Remember sample proportion, that's our p hat. Standard error, we just did that up there. It's the standard error of p hat. It's written like this. Well, this shouldn't be too bad. What proportion from our sample use social networking sites? Well, it was 1,200 used it. There were 2,500 that were total. So again, part over whole is how we do that. And when you reduce this, you're going to get almost half, 48%, 0.48. That's our p hat. This is our sample proportion. Now we also need to find the standard error. Okay, so the standard error, what was that? We have that formula. The standard error is based on, that's why this is on the inside of parentheses, because it's based on p hat. That'll just be the square root of p hat times q hat over n. Look, it looks like it's a little sad face. But you won't be making sad faces, I'm sure, while you're doing confidence intervals. It will be sad for you, or something like that. I don't know. So we know that p hat is 0.48. And we know that q hat is just what's left over. If 48% use it, then 52% will not be using it. And that's, again, we also have those formulas, right? Q hat is just 1 minus p hat if you prefer to use a formula instead. What was our sample size? It's not the number who agreed. It's the total number that we asked. Okay? So the sample size will be that 2,500. That's our n. And now we just plug everything in. P hat was 0.48. Q hat was 0.52. Divided by 2,500. And we'll type this into a calculator. You can use a handheld calculator. You can use the GeoGebra scientific calculator that's linked on Canvas. Either way, we'll just type this in. Oh, this window is very large. Make it a little smaller. And what we're going to get, SQRT for square root. Start the parenthesis to make this work. 0.48 times 0.52, end of the parenthesis, all over 2,500. Make sure it looks very close or exactly the same to what we want it to look like. Not all calculators do this, but GeoGebra does. And we get 0.009992. This is, normally I like to have 4 significant figures. Again, the 4 numbers after the zeros. But here, it just makes a lot of sense for this lesson to round this to 0.01. It's almost exactly 0.01. It's very close to 0.01, okay? So we'll have that as a standard error for p hat. That'll make it rounding this much, which normally is not a very good thing to do. But rounding this much here is going to make it a little easier for us to talk and visualize and introduce this concept. So now we want to draw the sampling distribution. Now we don't know the sampling distribution exactly because we don't know what P is, right? We need the population proportion P to find the sampling distribution. So we're going to approximate it. What's the best way that we have right now to approximate P? P hat. What's the best way that we can approximate the standard deviation? Our standard error. Okay, so we know that P hat is normally distributed with mean P. Assuming we have independence, randomization, and sample size conditions, you can check that we do have all 3 of those here. We have this, and then this is normally how we find our sampling distribution. Well, in this case, we don't know P and Q. We have to approximate it. All right, so we'll approximate it. with p hat, and you get this. And now we get something that looks a little strange because we're approximating p hat with p hat. It's a little circular in the logic. If we're really clear, these should be capital P's, a random variable. I'm just hard for me to specify what's capital P and what's little p. Capital P, little p. Okay. So that's how we'll do it. So we'll say that capital P hat is normally distributed with a mean of p hat, which was 0.48, and that standard error, because right, this is exactly our standard error of 0.01. Oops, 0.01, just like that. That's how our sample should look. Remember, the whole idea of a sampling distribution was every time we take a sample from the population, we're choosing random individuals. So every time we take a sample, we'll get a different sample proportion. There'll be on average some value, and on average, there'll be some amount of spread out. They'll be bell curve shaped as well. That's what sampling distributions are all about. So now, what does it look like? We draw a normal curve. It's centered at 0.48. One standard deviation above the mean is about where that curvature changes. That'll be 0.49, and then 0.50, and then so on. Remember that most of the data is within 1 standard deviation of the mean. Almost all the data is within 2 standard deviations away from the mean, and so on. We had that empirical rule, otherwise known as the 68, 95, 99.7% rule. And either way, this is what our sampling distribution model looks like. We should expect that when we take this sample, we're going to get a sample proportion of 48%. It would be really unlikely to take a sample and get a sample proportion of 51%, right? Look how unlikely that is. Look how small the graph is right there, okay? And that's what we've got. Okay, so I know this is getting to be a long introduction video, but we're almost there. Let's tie in a concept from Unit 5, normal distributions. We have the empirical rule right here. Where do we expect 95% of sampling distributions to fall? Well, the empirical rule says that 95% of sampling distributions are going to be within, or 95% of the values will be within 2 standard deviations of the mean. So 95% of all of these samples with our approximation should be between 46% and 50%. 0.46, 0.50. Let's answer the question first, and then I've got a secret to tell you, okay? I got a little surprise. So where do we expect 95% of them to fall? Between 0.46 and 0.50. So the surprise is that you just did, well, I just did, but you followed along your first confidence interval. That's what it's all about. We approximate with sampling distributions and say that, okay, we think 95% of the data is going to be within, oh, we'll use the empirical rule, or we're going to use something a little bit more precise later. And then we can say that 95% of the time, we can be 95, in other words, we could be 95% confident that the proportions are going to be between these two numbers. We'll get into interpreting confidence intervals in the next video, okay? So quick summary, we're not going to use this too much yet, but I'm going to show you what we actually did. This is how we find confidence intervals. We take our sample proportion, right? That's p hat, and we'll add or subtract a margin of error. That's this whole guy over here. And so this creates an interval of possible values. Confidence level is how sure we are. Usually one of these numbers. What do you think our confidence level was for this one. Yeah, 95% was our confidence level. Okay. We have some other terms that we'll use more later. This is just introducing it. Don't worry too much. Z star is something called a critical Z-score. Don't worry about that yet. 2 more videos, we talk about that. Not important right now. Margin of error is abbreviated MO. And yeah, that's our margin of error. Not super important yet either, but here's just an introduction. You've been exposed to it. You've done one. And then the next video will talk about how to, like, what does a confidence interval really mean? How can we use one? And then the video after that, we'll start actually creating them with this formula. We've already created one, but we'll do some more practice. So this is just an introduction. Let me know if you have any questions, and have a good one.